We now start our discussion on the module 3 of chapter 9. Recall that in chapter 1 and 2, we had extended the notion of length of intervals to Lebesgue measure in the set of real numbers. We had seen that Lebesgue measure is defined on a specific class of sets, namely Lebesgue measurable sets, which had the property that it is closed under difference and countable union. Now, we know that such a class of sets is called a sigma ring. So, the question arises that whether we can introduce the notion of length or measure in an abstract set. Obviously, we have to start first with the domain of the definition of this function or measure. We have already in the last two modules of this chapter have studied certain set theoretic classes, namely ring, sigma ring, monotone classes, and we are now ready to introduce the notion of abstract measure on an abstract setting. So, we introduce the formal definition of a measure. A measure mu is an extended real valued function defined on a ring R, which is non-negative countably additive with mu phi equal to 0. If for all members of the ring the value of mu is finite, then we say that the measure mu is also finite. The measure mu is said to be sigma finite if for any member A from R, we can find a sequence A n, n belonging to capital N from the ring such that A is contained in their union n equal to 1 to infinity A n, and each of the sets A n has finite measure. Let X be a set and let R be a ring of subsets of X. If we define mu A to be the cardinality of the set A, then it is easy to see that mu is a measure on R. This is called the counting or discrete measure. See that the discrete measure is not sigma finite on an uncountable set. On the other hand, we are already familiar with Lebesgue measure, and the Lebesgue measure is obviously sigma finite. So, first let us establish some basic properties of the abstract measure. These properties are same as the properties of Lebesgue measure, and we will not go into the details of the proofs of almost all the results. We will only go into the details of one or two results. Let mu be a measure defined on a ring R, then the measure mu is monotone and subtractive. The measure mu is countably subadditive. We will only give the proof of the assertion 2, because the proof was not presented during the presentation of Lebesgue measure. So, we start with a sequence E n, n belonging to capital N of sets from the ring R. Let us take a set E from R such that E is subset of union I equal to 1 to infinity E I. Observe that we can write E as union I equal to 1 to infinity E intersection E I. Note that since E and E I both belongs to R and R is a ring, so their intersection E intersection E I, if we write it as G I, then each G I belongs to R. Let us now put F 1 equal to G 1, F 2 G 2 minus G 1, F n G n minus union I equal to 1 to n minus 1 G I in this way. See that since we use only difference and finite union in each step, so each F n belongs to R, as R is a ring, and moreover the union of this new sets F I union I equal to 1 to infinity F I is the set E. Also the sequence F n, n belonging to capital N, is pairwise disjoint. So, using the countable additivity of the measure mu, we get mu E is equal to mu of union F I. This is equal to sigma I equal to 1 to infinity mu of F I, but note that from the construction each F I is subset of E I. So, mu F I is less or equal to mu E I. Hence, sigma I equal to 1 to infinity mu F I is less or equal to sigma I equal to 1 to infinity mu E I, and this proves the result. Next, we go to a result which we have already seen for the Lebesgue measure also, and we had also seen the proof. So, we will only state the result without going into the details of the proof. If mu is an abstract measure on a ring R, let E 1 subset of E 2 subset of E 3 be an increasing sequence of sets in R, then measure of limit n tends to infinity E n, that is the limit set of E n, is equal to limit n tends to infinity mu of E n, where as before we define the limit set of E n as union n equal to 1 to infinity E n. Similarly, we can show that if mu is a measure on a ring R and if E 1 contains E 2 contains E 3 be a decreasing sequence of sets from R, such that at least one of the sets E k has finite measure, then mu of limit n E n is equal to limit n tends to infinity mu E n, where as before again the limit set is defined as the intersection of all the sets. Now, we give the formal definition of outer measure. An outer measure mu star is defined as an extended real valued set function on a hereditary sigma ring H, which has the property that it is non-negative, monotone, countably sub-additive and mu star phi equal to 0. It is easy to note that the Lebesgue outer measure also had these properties. So, we have taken just those properties of Lebesgue outer measure. We have not taken the property of Lebesgue outer measure that it was translation invariant, because on an abstract set there is nothing called translation. Next, we are going to show that if mu is a measure on a given ring R, from the ring R we can generate the corresponding hereditary sigma ring, that is HR. Then the set function mu star defined on HR by the formula mu star E equal to infimum of sigma n equal to 1 to infinity mu E n, where E is subset of union n equal to 1 to infinity E n and each E n belongs to R. For any E belonging to HR is an extension of mu into an outer measure. So, in other words, we are going to show that if we have a measure on a given ring R, we can always extend it to an outer measure on the generated hereditary sigma ring. From the definition, it is obvious that mu star is non-negative, because we are taking the infimum of some numbers. All of the numbers are non-negative, and also mu star phi is equal to 0, because phi belongs to R and mu phi is 0. Further, note that if we take two members A and B from HR, where A is subset of B, then mu star A is less or equal to mu star B. The result follows from the fact that if we take a countable collection of sets E n from R which covers B, then as A is subset of B, so this collection also covers A. We are now going to prove that mu star is countably sub-additive. So, for that we start with a sequence of sets A n from HR. So, we have to show that if A is the union of these sets A n, then mu star A is less or equal to sigma n equal to 1 to infinity mu star A n. Now, see that if for some n mu star A n is infinity, then on the right hand side we already have the number infinity and there is nothing to prove. So, let us assume that for each n, mu star a n is less than infinity. Now, since mu star a I is less than infinity, so using the definition of Lebesgue outer measure, we can find a countable collection of sets E I j from the ring for a given epsilon greater than 0, such that sigma j equal to 1 to infinity mu star E I j is less than mu star a I plus epsilon by 2 to the power I. So, for each I, we have obtained a sequence of sets E I j from the ring with the property that it covers the set A I and the sum of their measures is less than mu star a I plus epsilon by 2 to the power I. Now, if we take the whole collection, that is E I j, where both I and j runs over capital N, then this being a countable union of countable sets is again a countable collection of sets from the ring R, and obviously union I equal to 1 to infinity a n is subset of union I equal to 1 to infinity union j equal to 1 to infinity E I j. So, from the definition of outer measure, we get mu star of union n equal to 1 to infinity a n. This is less or equal to sigma I equal to 1 to infinity, sigma j equal to 1 to infinity mu of E I j, and this is again equal to sigma I equal to 1 to infinity, sigma j equal to 1 to infinity mu E I j. We take these sums in the bracket, and this is less or equal to sigma I equal to 1 to infinity mu star a I plus epsilon by 2 to the power I, and the right hand side is equal to sigma I equal to 1 to infinity mu star a I plus epsilon. Since this is true for any epsilon greater than 0, so we have the property that mu star of union n equal to 1 to infinity a n is less or equal to sigma I equal to 1 to infinity mu star of a I. Finally, we want to show that mu star is an extension of mu. For this, we take a member E from R. If E is subset of union n equal to 1 to infinity E n, where E n belongs to R, from the property of abstract measure, mu of E less or equal to sigma n equal to 1 to infinity mu of E n, and consequently, we must have mu E less or equal to mu star E. Again, see that we can cover E by E union phi, union phi, union phi in this way. And from the definition of mu star, mu star E should then be less or equal to mu E, because by our assumption mu of phi is equal to 0 from the property of measure. So, we have mu star E equal to mu E for all E belonging to R, and this shows that mu star is an extension of mu to an outer measure. Next, we introduce the formal definition of measurable sets. Again, this is same as the definition of Lebesgue measurable sets. A set E belonging to H R is called mu star measurable or simply measurable when there is no confusion if for any A belonging to H R, mu star A is equal to mu star A intersection E plus mu star A intersection E complement, where E complement stands for the complement of the set. These observations are easy and actually they are exactly similar to the observations for Lebesgue measurable sets. If E belongs to H R with mu star E equal to 0, then E is measurable. E and F measurable implies that E union F and E minus F are measurable. If E n is a sequence of pairwise disjoint measurable sets, then for any A belonging to H R, mu star of A intersection union I equal to 1 to infinity E I is equal to sigma I equal to 1 to infinity mu star A intersection E I, and their union E is measurable, and from that it follows, like in the case of Lebesgue measurable sets, that countable union of mu star measurable sets is also measurable, and consequently the collection S bar of all mu star measurable sets is a sigma ring. Now, we want to show that every member of the original class R is mu star measurable. Let us choose any arbitrary member E from R. Take any set A from H R. Let epsilon greater than 0 be given. Now, from the definition of mu star A, we can find a countable collection of sets E n from R such that A subset of union n equal to 1 to infinity E n and mu star A plus epsilon is greater than sigma n equal to 1 to infinity mu E n. Now, E n can be written as E n intersection E union E n intersection E complement, where both the sets belong to R. So, we can use the additivity of the abstract measure mu. So, we can write the right hand side as sigma n equal to 1 to infinity mu of E n intersection E union E n intersection E complement, and this is equal to sigma n equal to 1 to infinity mu E n intersection E plus sigma n equal to 1 to infinity mu of n intersection E complement, and this is again greater or equal to mu star of A intersection E plus mu star of A intersection E complement, because the collection of sets En intersection E covers A intersection E, whereas the countable collection of sets En intersection E complement covers A intersection E complement. Since this relation is true for any epsilon greater than 0, so we get mu star A greater or equal to mu star A intersection E plus mu star A intersection E complement, and this shows that the set E is measurable. So, to summarize, what we did in this module is that we have formally defined the notion of abstract measure as also the notion of abstract outer measure on a ring and on a hereditary sigma ring respectively. We have seen the basic properties of the abstract measure, and we have also seen that given an abstract measure mu on a ring R, we can extend it into an abstract outer measure mu star on the generated hereditary sigma ring H R. And in the last result, we have seen that every member of R is mu star measurable, where the notion of mu star measurable sets is defined in the same way as Lebesgue measurable sets, and they have the same property, that is they form a sigma ring. And with this we end this module.